to tell us again about the aperiodicity of the primes. I hope that we at last get it with his twin beer mat. We've got the summary. I was looking for this. Oh, they're there. Welcome, Grenville. Thank you.
Thank you, Nicola. Just a bit about this presentation arises from a piece of work I've been doing for about 5 years on a thing called bientropy, and I managed to get it published. So I did bientropy in the primes and presented that here in Liverpool 2019, and I managed to get it published in 2020, just as we went into its lockdown. So I managed to get it published in a math sci-net rated journal, which is a good place to get published. And nothing really happened for 2.5 years until November, when I got my first citation. And so the bientropy and primality work has now been cited about half a dozen times, including once in a article published by the American Institute of Mathematical Sciences. The work is starting to slowly get accepted out there in the academic world. I decided to do the work again and strip it back to its basics, because I wanted to make sure that people really understood, the fundamentals of what I was doing, because it relates to the numbers, which of course we all use all the time. Those are the things I'll cover as quickly as I can. I'd like to really focus on the experimental results, which are really quite interesting, in fact rather surprising, I believe. I've done some more recent work on asymptotes to show that how things work as we take our numbers to infinity. This is a profoundly simple result, but basically if you have a number in any base where the digits repeat, with one exception, that number cannot be a prime number. So 1101, 1101, that can't be prime. 7373, 7373, that can't be prime. It doesn't matter whether that number is in base 10 or base 20 or base 21. That number cannot. Numbers with repeating digits cannot be prime. And so there's the proof, profoundly simple, and it's arising from the fact that because you've got a repetition, there's an element of two-ness. So I know that in ANPA work, 2 has been a interesting number. Peter Rowlands has done a paper on two-ness, and here we find right in the origins of number theory that two-ness, periodicity, cannot be prime. So there's our exception. So when the two halves of the number are simply 0, 0, 1, I've got 1 in them, whether it's as simple as 23, which is so where numbers, where the two halves are equal and they're equal to 1, the number may be prime. So I mean, the examples there is 0101 in base 6, that's 37, and 37 is a prime number. Second example I give is 0101 in base 10, which is 101, and that is prime. So that's our exception. And so what pops out is something rather surprising, which is that if we look at all these periodic numbers, 16 of them, we find that we've got the 17 times table. So out of periodicity pops the 17 times table, which is quite interesting. So because we're in binary, in binary we have these things called n periodic numbers, and And this is where the first part of the number is the ones complement of the second part of the number, and vice versa. So this number here, 10100101, that is the first part, 1010, is the ones complement of the second part, which is 0101. And n-periodic numbers, they can't be prime either. And the proof is straightforward and as simple as the previous proof I just gave. So here are the n-periodic numbers. And hey presto, the 15 times table pops out. So here are the 16 periodic numbers that are 8 bits long, and they enumerate the 15 times table. So we haven't done any division yet, we haven't done any multiplication yet, but here we find the 17 times table and the 15 times table. So I needed to also define what's known as the Z-periodic numbers. This is a number that's got an even number of zeros at its head. So here we have a Z-periodic number. It's periodic with length. So 101, is periodic with 2 zeros at the front of it. So that's what we call a Z-periodic number. And they can't be prime either. So here are all the 8-bit Z-periodic numbers, 4 leading zeros, 2 leading zeros. First case we get 5 times table. Second time we get 3 times table. So this is the essence of periodicity. Now we can detect periodicity in a number by using the binary derivative. So here's a number s, and here's its first binary derivative. So to calculate the binary derivative, we start at the right, and we write it as 0 if the 2 digits are the same. If the 2 digits are different, we write a 1. So 2 digits the same, write a 0. 2 digits the same, write a 0. 2 digits different, write a 1. 2 digits different, write a 1, and so on. And so there are a series of binary derivatives that get 1 shorter until the final binary derivative is either a 0 or a 1. And so we can use the binary derivative to determine whether or not a number is prime because of theorem 2, which is by a guy called Mervyn Nathanson, who did a paper in 1971, which it's hardly cited at all. There's a beautiful proof in there that shows that a number is periodic with a period of 2 to the power of n, if and only if for some k there is a derivative that's all zeros. So if you look at if you think of all the binary numbers, of which there are infinitely many, if any of the derivatives of a binary number are all 0, then that number is at risk of being prime. It doesn't if a binary derivative is 0, it doesn't necessarily imply that the number is prime. But a number that is prime will have a 0 binary derivative. A number will be periodic if it does have a 0 derivative. So there's another theorem which is pretty useful, theorem 3. As we compute the bits of a derivative, the bits themselves are uncorrelated and are statistically independent of each other. So as we calculate the series of binary derivatives, there are no significant patterns either in amongst the digits of the binary number itself, or indeed between the derivatives. So when we compute the binary derivatives, it's not knowable in advance any patterns that are going to appear. Everything's statistically independent. So theorem 4 is that successive binary derivatives are independent of each other. That was proved by Davis et al. in 1995. So some more interesting properties. Every binary number is the binary derivative of exactly two numbers one bit longer. Related to that is theorem 5b, which is the pair of binary integrands for one's complements of each other. And that's very simple to demonstrate. So here are the 8 3-bit numbers, and 0, 0, and 1, 1, 1. Those differentiate down to 0, 0, 0, 1, 1, 1, 0, differentiate down to 0, 1, and so on. And so you can see there's an exact correspondence in number between the binary derivative or the binary integrand. And that causes the symmetry of a diagram which will follow shortly. So the last little theorem is that if the binary derivatives, if any binary derivative is all ones, then the next binary derivative will be 0. And that causes a little formula to become nicely exact. So we can now do a computer measure, or develop a measure that reflects the probability that some number is prime, basically by looking at the binary derivatives. So let PS not prime be the probability that a number is not prime due to its periodicity, its M periodicity, or its Z periodicity. So alternatively, let PS prime be 1 minus PS not prime, its converse, the probability that a number is prime. And so I've devised this quantity, PS prime, which is based on the binary derivatives, that tells us the probability that a number may or may not be prime, based purely upon the observed patterns in its binary derivatives. And that's the formula that does it. And so what we're doing is we're rounding up for all the binary derivatives, a weighted average of whether or not each derivative is prime. It is periodic, plus a little rounding factor, which makes all the numbers exactly divisible by 2, as it happens. And so, like doing things in spreadsheets, this is how we calculate the probability of a number being prime. So there's 23 in the green. That's the 1s and 0s corresponding to 23. Here are 1, 2, 3, 4, 5, 6, 7 binary derivatives, ending with a single last binary derivative. And that's the calculation. And you can see that the probability of 23 being prime, based upon only the pattern of its binary derivatives, is 0.5. So we know that 23 is a prime number, but we don't care. What we're wanting to do is come up with some measure that tells us, based upon the patterns in the binary derivatives, whether or not this number might be a prime number. Everyone with me? Yeah. And so here's a tabulation of the 256 the first 256 numbers running from 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, all the way up to 256, which is 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. So I put these in a particular order just to emphasise the symmetry. And so you can see that most of the prime numbers, which are coded purple, are in these 2 quadrants here. There's only one prime number on the diagonal. So you can see that the PS prime varies between 0 and 1 in some chunky steps like 0, 0.25, 0.5, 1.0. So for every number between 0 and 256, we get a number between 0 and 1, which tells us the relative likelihood that the number's prime or not. And of course, this diagram applies to the infinity of numbers because we can differentiate down every number of whatever length into the last 8 binary derivatives, and we can tabulate the numbers of primes in each of these 2, 5, 6 categories if we wish. But this encoding is the actual primality of the first 255 numbers. And so the prime number theory was developed in 1896 by 2 French guys, Hadamard and Grenville-Croll, and we can now modify the prime number theory to say that the number of prime, the probability that S is a prime number is called Ls multiplied by PS prime divided by 2S. So the prime number theory gives us used to just give us the number of primes less than X or less than X, but we can now modify that to give the probability that a number is prime based not only upon its magnitude, but based also upon the patterns of its binary derivatives. Or if the lower numbers, where we can enumerate exactly the number of primes less than X, less than S, there's an equality. So the probability that S is a prime number is exactly equal to pi of S multiplied by PS prime, etc. So Ls is the approximation, and pi of S is exact. So we decided to go and first of all do a simple experiment, which is to look at all numbers between 0 and 2.5 inclusive, and tabulate how many are prime and how many are not prime based upon PS prime. So here's 2 by 6. There are 54 primes that are less than 2 by 6. There are 6,542 primes that are less than 65536, and so on. And so we can, based on the fact that we know exactly how many primes there are in each of these categories, because we can simply count them, we can make our a priori expectation of how many primes there are in each category. And here's the actual number of primes by PS prime. So we find of the 6,542 primes that are less than 65526, we find there's 3,588 are in PS prime as well, and 1,673 are in the category PS prime equals 0.5, and so on. So here, 2 by 6, we know there's 54 primes less than 2 by 6. We find 38 are in PS prime equals 1, and only 11 in PS prime is 0.5. And so there's a difference between actual and expected, which was a surprise. We were not expecting this. Prior to 18 months ago, I'd never done this calculation, and I was expecting that the number of primes in each category would be equal, but that's not the case. And what we find is that there are an excess of primes in this category compared to all the other categories. And you can see that the analysis is very sensitive. So this here, the difference of 1 between actual and expected, that corresponds to the prime 17, which is a Fermat prime. You can see here 257 is Fermat prime, which is one of the exception I mentioned. That causes this here. So the analysis is very sensitive, and you can see that the primes that's in 65536, there are 355 extra primes in these two categories compared to the other categories. That bit of red corresponds to Fermat primes 3 and 5. So very sensitive analysis, which was not expected. So if we graph the numbers of primes in the various categories, you can see that they're essentially quadratic. And you can see that red line corresponds to 6542. Where's that happening? And if we take the log of that graph, you can see that they are everything's nicely parallel, apart from early doors with the lower numbers. Everything settles down, and so because we've designed PS prime to be quadratic, we expect it to be quadratic, and indeed it is quadratic. And the purpose of doing this whole piece of work was to emphasise the fact that we can take the primes from the natural domain, put them into a quadratic domain, do some interesting work, but then transform them back into the natural domain, having investigated their properties in the quadratic domain. And so we can plot what's known as the prime density, which is the cumulative number of primes by PS prime. So this top line purple is the natural domain, which is logarithmic, and PS prime is in the quadratic domain, which is the lower line, and one of the lines is a quadratic curve fit. But you can see the quadratic curve fit isn't perfect, and that's because PS prime is very lumpy. The previous function, by entropy, that was much smoother. And so this is the error between PS prime density and quadratic, and you can see it's binodal, and in fact it's binormal. So here you can see that it's symmetric about 0, and we can see here the relatively small variation between natural and expected primes, all the way up to 65536. So there is only a small error in the quadratic. And so, in trying to describe all this, I came up with this nomenclature. And so, if PS prime is close to 0, the number probably cannot be primed, because it's either periodic, n-periodic, or z-periodic. If PS prime is 1, then the number may be prime, because no binary derivative is 0. Or alternatively, if it's between 0 and 1, it may not be prime, because one or more binary derivatives is 0. So, some numbers cannot be prime, some numbers may be prime, and some numbers may not be prime. And so that's just simple arithmetic relationships. All the numbers are either prime or not prime. All the numbers either can be prime or cannot be prime. And can be prime plus cannot be prime is exactly equal to may be prime and may not be prime. And the relationship between may be prime and may not be prime is approximate in the lower numbers. As we'll see later, it's exactly, the proportions are exactly equal as we approach the limit. And so the actual number of prime numbers is prime total integers, expected prime is linear total integers. And this is the important quantity, which is the difference between the difference between so excess maybe prime is equal to actual maybe prime minus expected maybe prime. So we're reflecting. So excess maybe prime is the difference between these two quantities. And so this is the more recent work. It is certain that cannot be prime is an inverse quadratic function of the number of primes, and so that converges to 0 as a proportion, and excess maybe prime also converges to 0 as it must, which I'll show you in the summary. And so, since speaking last time, I did a Monte Carlo simulation at 32 bits. So all the work I've just shown you was just 8 bits and 16 bits. So I've now gone and investigated numbers which are 65,536 times as big to go and see if we get the same results. And basically I do. So around 2, 4, 6, 8, 10 simulations of 2,000 observations. So basically I investigated 20,000 random numbers that were 32 bits long. And we know that about 4.75% of them should be prime. And so, hey presto, across the 10 simulations, we find that the numbers that may be prime and may not be prime match very closely, and the numbers that may be prime that are indeed prime, and the numbers that may not be prime and are not is similar. And so we've got we've got convergence of our results at in the higher numbers. So since this is the excess, these two parts are equal. So excess may be prime contains all the variation in the difference between our expected primes and our actual primes. And yeah, so excess may be prime contains all the variance of the difference between pi x and the x. And these two quantities must be equal in the limit. And so we basically get a repeat of our earlier results from years ago, which is in the limit. The variance of the difference between pi x and the x must go to 0. So that's what we've done. We introduced a scale invariant theory of periodic numbers. I worked for all numbers at whatever scale. There's 9 theorems apply for all numbers. We've got a proof that the prime numbers are aperiodic with one exception. Demonstrated primes must behave according to these theories and limit and provide a nomenclature around the primes. And so we've been working in the quadratic domain, doing some experiments and showing some different things. And we can translate that work into the natural domain quite easily. So, any questions?
Yes.
Oops.
So my first question is basically, since the binary definition of the binary derivative is based on the x exclusive OR, is that what I understood you say? Okay. So does that mean that you were saying something was statistically independent and uncorrelated? Is it because of that basic definition of the exclusive OR that the binary derivative?
No, there are 2 proofs. it doesn't directly follow that that's the case. There's two proofs, one by both by data set out. So they take the algebraic property of the binary derivative, and using a series of deductions, they show that the bits are independent and the successive derivatives are independent.
So there's two independent things going on.
Yeah. And it's related very strongly to the halting problem. So what it means is that you've got a long number. It's not knowable what the final binary derivative is. You've got to go and compute all the derivatives to find that answer. So that's a variation of the halting problem.
And the second question was, is there a relationship between aperiodicity and stochastic randomness in general, or are you saying that?
Well, if a number is periodic, is it random?
No, it's not. I'm saying it's aperiodic. Is aperiodicity like the randomness? Is that correlates to stochastic randomness?
Well, that's a big question of the time. That's a big question of our time. So, is this PS prime function I've just invented, and it's related by entropy function, with which it's strongly correlated? How do they relate to entropy, and how do they relate to randomness? What is entropy? What is randomness? And what's the relationship with these to that? So there's lifetime's work there.
So that could be like so the aperiodicity could be like a definition of random?
Yeah. So, and the big clue there is that, firstly, the US government filed a patent that includes by entropy as the filter to make sure that the random numbers coming out of their random number generation chips are indeed random. But then if you change the random number to base 3, by just doing simple arithmetic conversion, and then you observe the periodicity in base 3, is that number that you thought that was random in base 2, random in base 3? And how does that affect its randomness?
Right. I didn't. The first part of the talk said something like in every base except a certain one, something was periodic or something was.
Periodic numbers can't be prime in every base, with one exception, and the exception is that if the number is represented as a 1 and a 1, it may be prime.
So you're talking about unit base 1?
No. So 23 is a prime number, yeah? So in base 22, it's represented as 1, 1.
Right.
So every number can be represented as 1, 1 in at least one base.
Oh.
Yeah? Okay. So the number can be represented in any base as 1, 1. It may be prime.
Oh, I see. I didn't finish that. Okay.
Yeah. So, 2B in that summary? Yeah. So, which side do you want? The green side or the red side? The red side. So, these two beer mats represent the infinity of numbers. Yeah? And there's two halves to that infinity. There's the half of the infinite number that just have a final derivative of 0, and the other half has a final derivative of 1. And the two halves are exactly equal. They're exactly the same number of numbers with final derivative 0 and final derivative 1. But it's slightly clearer than that, if you'll forgive the expression, because there's a gap. So that the numbers at the top, where the beer mats are touching, and they're touching, I'm pressing hard against the two beer mats, it's the numbers close to infinity that's at the top. Yeah? And at the bottom is the lower number of integers. So let's talk about at the bottom. Let's assume that's integers that are close to 256. Well, there are 54 prime numbers that are less than 256. And as it happens, 38 of them may be prime. And 12, I think it was, may not be prime. So it's till is slightly tilted, slightly skewed, and we weren't expecting that. We were expecting the actual number of primes that were in the gap would be exactly divided between maybe prime and may not be prime, and that was a surprise. And it was not expected. But what it helped to do is emphasise the fact that the excess of the difference between what we were expecting also contains the variance in the number of primes. Because from the prime number theorem, we don't know exactly how many primes there are below x. For a very large x, we only know approximately. And so excess may be prime, which is the difference between the expected number of primes and the actual number of primes. It also contains all the variance. And because we know from theory of large numbers or sampling theory or whatever, that these two must touch at the top. And so that implies that the excess of the difference between the actual and expected must go to zero as a proportion. And to support that, we've got 9 theories behind us that tell us about the binary structure of numbers. And so basically having now written up that piece of work, that's now my second proof that the difference between pi x and the x goes to zero in the limit. So not only have I done it once, I've done it twice by 2 different methods. The first method is to show that the quadratic has nil error in the limit. And the second method is the 2-Beermat method, which is probably about the simplest way you can possibly describe something. Thank you.
You did that demonstration in your local team.
I've done it to my 9-year-old. Yeah, I've watched I've got a photograph of my 9-year-old taking the full set of derivatives of an 8-bit number, having taken him through the decimal to binary and binary to decimal conversion. So, thanks for that.
Okay, so let's have a look. So, is there anybody on Zoom who wants to come in at all? I don't see any hands up.
No handing here from Michael.
Okay, thank you. So, shall we go straight on now, or should we just do like a 5? I can see
a short break.
A short break. Okay, we'll have a short break, and then I'll chair again.